This is Unit 11, and this is going to be a lesson on how to draw organic structures, structural models, and how to name organic molecules using the reference tables that the state gives you. Those reference tables are P, Q, and R. So P, we've gone over this already if you've watched previous lectures, number of carbons. So the more familiar you are with those 10 prefixes, meth, eth, prop, but, pen, hex, hep, doc, non, dec, those always refer to numbers of carbons in the name. And other prefixes, when you see mono, di, tri, or tetra, that's going to mean number of pieces. So trimethyl means 3 groups that each contain 1 carbon for a total of 3 carbons. Reference table Q were for the hydrocarbons. Those are the things made with just hydrogen and carbon. Alkanes, alkenes, alkynes. The ending of a name of something that is an alkane chain, something that has all single bonds between the carbons, ends in A-N-E. Alkenes have 1 double bond, E-N-E. Alkynes have 1 triple bond, Y-N-E. One of the common mistakes is people want to put every bond between carbons as a double bond with the alkenes. There's only 1. If there are 2 double bonds in your carbon chain, then it would be a diene. It would have a different name. We're only being tested on these 3 classes of hydrocarbons, not every hydrocarbon. So you are never going to be asked to draw something that has more than 1 double bond in between or more than 1 triple bond in between, just the alkenes and the alkynes. And then, of course, reference table R was kind of our dichotomous key for all of the rest of it. You're looking for what's different on there. Halides have a halogen in them, something from group 17. Prefixes fluoro, chloro, bromo, iodo. Those should be familiar to you because we've used the halides a lot this year. Almost everything else has oxygen in it. The amines and the amides down at the bottom with nitrogen. So if something kicks up and it has nitrogen in it, it's going to be one of those 2 groups. The other ones with the oxygens, you're thinking, is there 1 oxygen or 2? Are the oxygens on with double bond or single bond? Keep narrowing your choices down, and we talked about using it like a dichotomous key if you watched the lecture on the reference tables and in class. For the alkanes, the alkenes, and the alkynes, and for the halides, one of the easiest ways for me to explain the naming rules is to show you how to draw them, because the names are a pattern. The names are instructions for how they're drawn, so that's how we're going to do this, is by example. So if we look at this first one and we take the name apart, heptane, hept, we know from table P, means 7 carbons, and ane, we know from table Q, means all single bonds. So all we have to do then is draw 7 carbons, 1, 2, 3, 4, 5, 6, 7, all single bonds between the carbons, and now we need to add hydrogen so that each carbon has 4 bonds total. So we have a total of 16 hydrogens altogether. Heptane's formula, if we use the general formula from table Q, which is CnH2n plus 2, should be C7H. 7 times 2 is 14 plus 2 is 16. We count our hydrogens and our carbons, and we have the correct number, so we know that this is right. The state is going to require you to draw all of your hydrogens on, or draw it like this. Both of these would get you credit. On our exam, if you draw a single line sticking out like that with nothing written on it, the assumption is that you have a hydrogen attached to it. As you look on the web or you watch other videos, there are other ways of drawing these molecules, but the state will not give you credit for them. So make sure you're using one or the other of these 2 choices. Write the hydrogens, or at least have the lines. Moving on to the next one, 3-octene. So we're going to pull this name apart again. Let me switch colors. Oct means 8 carbons. Ene, according to table Q, is the ending for an alkene. So it's going to have 1 double bond on it. It has the general formula CnH2n. So that means I need 8 carbons and 16 hydrogens, and I have to figure out how to draw it. And I have this one extra thing left over. I have a number. What the number is going to tell you is a location. Anytime you see a number written out, not as a prefix, not as a word, but an actual number symbol itself, that's going to be the location of whatever is different or special about this compound. So what's different or special about octene is where the double bond is. So this means the double bond is going to be on carbon number 3. So when we draw structures, I'm going to draw your 8 carbons. We're going to number the carbons. So pick an end and number them. This would be carbon 1, 2, 3, 4, 5, 6, 7, 8. You don't have to write the numbers in. I'm writing the numbers in to show you where the numbers are. Carbon number 3 has the double bond. Now it's going to look like you have 2 choices for carbon number 3. How do you know which one? If I put the line here, don't do this, this is wrong. That bond is between carbons 2 and 3. When we put numbers, we always use the smallest number possible. So if the bond was there, that would be on carbon number 2. Right here, where it's between carbon 3 and 4, and we use the smallest number, this double bond is on carbon 3. Then we just add hydrogen, so everybody has the proper number of bonds. You'll see I erase the numbers because when we draw final structures, we don't put the numbers on. It looks very similar to our octane up here, except for where the double bond is. And note that the carbons that have the double bond already had 3 bonds, so they only needed 1 hydrogen each. Make sure you're not putting hydrogens all the way around. That's a really common mistake. You should always double check and count that each carbon has the correct number of lines and that you have the proper number of carbons and hydrogens. I want to point out something else to you about the counting, so let me draw another chain of 8 carbons. When we count, molecules don't have left or right sides, so we could count from the left, 1, 2, 3, there's your double bond, or we can count from the right, 1, 2, 3, and your double bond would be right here, and then hydrogens around. So that your molecule looks like this. There's one more thing that people ask, so let me show you one last version of this. The only thing different about this one is where I put the 2 hydrogens. Now on the other ones, I put 1 hydrogen on one side of the double bond and 1 on the other side of the chain. You could put them both on the same sides of the chain. People ask me, is there a difference? And the answer is both yes and no. Yes, technically, if we were in college and this was an organic chem test, they would tell you whether you were going to put them on the same side and they refer to them as cis, or on the opposite side and they refer to that as trans. But this isn't college, it's high school chemistry, and for our purposes, they mean the same thing. It doesn't matter. Moving on to things with branches. 2-methylpropane. Prop means 3 carbons. ANE means all single bonds. Meth means 1 carbon. All right, let's see what we have left over. Oh, a number. We have a number 2. We know that that means a location. And the only thing left in this name then is this lovely YL right here. YL is going to mean a branch. That's going to be an open bond that doesn't have a hydrogen on it, so it's going to have to be attached to another carbon. So if we draw this end part here is the part we're going to draw first. They call that your parent chain. So that's the basic of our compound, our backbone, and our backbone is 3 carbons long. 1, 2, 3. All single bonds between the carbons. This 2-methyl tells me on carbon number 2, I have a branch that is 1 carbon long. So I put a branch on carbon number 2, and I put a carbon, and then I add hydrogens around. And 2-methylpropane would look exactly like this. You could also draw it this way because those are the exact same thing as just a mirror image. These are the only two ways you can draw 2-methylpropane. So the instructions will tell you exactly what the molecule should look like, and this way all chemists know exactly what it is they have. One last hydrocarbon, and then we'll move on to halides. 3,3-dimethylnonane. So non means 9 carbons. ANE means all single bonds. 3,3 is the location. Di is a different prefix here. We haven't used this yet. That means 2. Meth we know means 1 carbon, and the YL was a branch. So I have 2 branches that are 1 carbon each. On a chain that's 9 carbon longs total, and those 2 branches go on carbon number 3. So it's going to have a parent chain, a backbone that looks like this. So there's my 9 carbons. I'm going to count from the left because we read from right to left. So that's typically where we're going to put them. 1, 2, 3. Here's carbon number 3. It needs 2 branches. Now when they say 3, 3, I can't put them both on the same side. If I put a carbon here and then a carbon on the branch, you're going to end up with just 1 branch that's 2 carbons long, and it would be called ethyl. So instead, we're going to put it on 3, 3. That means each of the open bonds on carbon number 3 gets a branch, and then hydrogens around, so your final looks like this. And of course, you could mirror image that, and your molecule would look like this. So the words in the names, instructions for how to draw them, we're going to move on to halides. When you see a name and it contains one of the halogens, so hopefully at this point in the year you're familiar enough with the elements that fluorine, chlorine, bromine, and iodine are familiar to you. That's the halogen group, group 17. So when you see chloro, you should think chlorine and Cl. Go to reference table R. And the very first category here are the halides. So fluoro means a fluorine, chloro, chlorine, bromo, bromine. And then look at the name that they give you. So when you have something that's a substituted hydrocarbon, there's something in there other than just carbons and hydrogens, use table R and look at their example to help you figure it out. Now on reference table R, their formulas are expanded molecular formulas is how they refer to them. Each of the carbons is a carbon in a chain, and they tell you what's on it. So this carbon has 3 hydrogens. This carbon has a hydrogen and a chlorine. This carbon has 3 hydrogens. So if you were to draw that, CH3, CHCl, CH3. So the expanded molecular is telling you what to do in each part of the chain. Then I want you to look at the name. So the name says 2. We know that's a location, and oh look, there's carbon number 2 right there. Chloro, carbon number 2 has a chlorine on it. Propane, prop means 3 carbons. There's 3 carbons total. ANE means single bonds between your carbons. So you can look at the 2, and it's giving you instructions for how you're going to name these guys and how you're going to draw them. So if we go back to our problem, this one says 1, 2. So those are going to be our locations. So those are carbons 1 and 2. Dichloro, so I have 2 chlorines. Bute, 4 carbons. Ane, all single bonds. So 1, 2, 3, 4 carbons. On carbon 1, there's going to be a chlorine. On carbon 2, there's going to be a chlorine. And then just hydrogens all the way around, so everybody has the proper number of bonds. Again, other ways that would be acceptable to draw it would be to put the chlorines on the other end of the chain. You could also put them on the same side. all going to be the same thing for our purposes. These would all be 1,2-dichlorobutane for what we're asked to do. This next example, 2-chloral. So on carbon number 2, there's a chlorine. 3-fluoryl. So on carbon number 3, there's a fluorine. Hex means 6 carbons, and ane means all single bonds. So 6 carbons, all single bonds. On carbon number 2, there's a chlorine. On carbon number 3, there's a fluorine. And then, of course, your hydrogens all the way around to finish off your molecule. The names are instructions. Follow the instructions, and you'll draw the structures correctly. Now I want to spend some time using reference table R to name molecules. So your first step is going to be to pick out which class of compound you have. Hopefully you watched the lecture on reference table R so you know how to do this. So the first one, 1 oxygen single bonded on OH on the carbon. So 1 oxygen is an alcohol, ether, aldehyde, ketone, single bond leaves me with alcohol and ether. OH means it's an alcohol. So now that I know it's an alcohol, I use the formula that they gave me here as an example. So they have their expanded molecular, and I can see each link in the chain. So CH3, CH2, CH2OH, and they're calling it 1-propanol. So the 1 must refer to the location of the OH since that's the functional group. The prop must be the total number of carbons, 1, 2, 3. The enol must be the ending for an alcohol. So if I go back to my example, I have 1, 2, 3 carbons, so that's prop. I know it's an alcohol because of this group, so it's going to end in enol. And the location of this OH is not carbon 1, it's on carbon number 2, so this one is 2-propanol. It is an isomer of the example on table R. 1-propanol, 2-propanol isomers. Next, I have 1 oxygen, single bonds, COC. So 1 oxygen, single bonds, again, alcohols or ethers. So this must be an ether, COC. Look at their example. CH3O, CH2, CH3. So CH3O, CH2, CH3, that's what it's going to look like. They're calling it methyl, which means 1 carbon, ethyl, which means 2 carbons, and they're ending the name with an ether. So if I look at my example, where there's 1 carbon is right here at the end. There's 1 carbon. Ethyl, 2 carbons. Here's 2 carbons, and they're calling it an ether. The functional group is an oxygen holding a chain together, so this must be what makes it an ether. So all they've done are name the branches. The only thing you have to be aware of is that they're going to name the branches in order of size. Smallest branch first, largest branch second. It doesn't matter if I draw it this way or the way that I drew it in the first place. These are both going to be called methyl, ethyl, ether. Always name the smallest branch first. So back to our example. I split the ether where there's an ether, so I know the ending of the name is going to be ether. This branch has 2 carbons. Table P tells me that's F. This branch has 4 carbons. Table T tells me that's but. F is the smaller of the 2, so that's going to go first. Ethyl, butyl, ether. Moving on, C, 1 oxygen. The oxygen's held on with a double bond, and it's on the end. So table R tells me that 1 oxygen double bond on the end is an aldehyde. We look at their example. CH3, CH2, COH, see double bonded OH, and they named it propanal. So prop, 1, 2, 3, there's 3 carbons total. Anal must be the ending for an aldehyde. 1, 2, 3, 4 carbons total. The prefix for that is bute from table P, and we're just going to end it with an al. So naming aldehydes is very easy. The only thing I want you to be very careful of is the ending and your handwriting. I'm writing quick here, so it's not the neatest, but on the final, the only difference between the ending for an alcohol and the ending for an aldehyde is whether it's an O or an A, and if somebody who hasn't been reading your writing all year long can't read your writing and can't tell the difference between whether it is an O or an A, you are not going to get credit for it. So make sure your handwriting is legible. Next, I have a double bonded O in the middle of a chain. So it's bonded to a carbon, and that carbon is bonded to two other carbons. Reference table R tells me that's a ketone. I look at their example. CH3, C with the double bonded O, CH2, CH2, CH3, 2-pentanone. So pent I know means 5 carbons. There's 1, 2, 3, 4, 5 carbons total in this chain. Anone must be the ending for a ketone. So all I have left is a number. The number is going to tell me the location of the functional group. So it's going to tell me where that double bonded oxygen is. Just know that ketones have to be at least 3 carbons long. If it's smaller than 3 carbons, it will automatically make it an aldehyde because you can't put the double bonded O in the middle. So all I have to do is count the number of carbons, add a known, and then put a number for the location of the double bond. Count the carbons. 1, 2, 3, 4, 5. 5 is pent. It's a known. And the location of that, now be careful, you got to count from both ends. It's either 1, 2, 3, 4 or carbon 1, 2, and we always use the smallest number, 2-pentanone. This one, 2 oxygens, O, COOH, C double bonded O with a hydroxyl branch. Hopefully by now you know with the YL ending that's why we call this a hydroxyl and not a hydroxide, because it is a branch on a carbon chain. So that is an organic acid. Their example, propanoic acid. Prop we know means 3 carbons. Anoic acid must be the ending for an organic acid. CH3, CH2, COOH. Here's my functional group. No numbers needed. Count the number of carbons. Add anoic acid. Nice and simple. So this one has 1, 2, 3, 4, 5. 5 is pent. And you just add anoic acid. Nice and easy to name those guys. And then last but not least over here, we have an ester. So I have COOC. Here's my functional group right here. A carbon with a double bonded oxygen with a single bonded oxygen who happens to be attached to a carbon. So this is an ester. The example on your table of an ester is this methylpropanoate. So meth means 1 carbon and the YL means a branch. Prop means 3 carbons, and then we have anoate for our ending. So this must be what tells you it's an ester. When I look at my example, and I'm going to draw this one out. When I look at this, I'm going to start splitting it up. There's 1, 2, 3 carbons in the part that has the oxygen, and then just 1 carbon left over. So this methyl must refer to whatever branch is on the oxygen. The first branch part is the branch on the oxygen. The prop, meaning 3, must mean this chain of 3 carbons. So the carbon chain that has the oxygens on it, the double bonded oxygens, goes with the anoate. The branch that's single bonded to the oxygen, just the 1 oxygen, is the branch at the beginning. It's not always going to be smaller first in this one. The esters we'll talk about a lot more in the lecture notes, and I'll explain how these guys are formed. For right now, when you look at an ester, split it so that one side has your double bonded OO and the other side is a branch on that. So we're going to name the branch first. This is 2 carbons long, so that's an ethyl branch. Then we're going to name the rest of this. 2 carbons is F, and then you add a NO8. Just know how to recognize the amines and the amides down here. Amines and amides, the amine with the nitrogen on there that has 3 attachments to it. These could be carbons, they could be hydrogens. The only tricky thing with the amines is sometimes you'll see something like this, and it throws you off because now you have a nitrogen and carbons and 2 oxygens, but it's not an amide. An amide has a nitrogen and 1 oxygen. This guy has 2 oxygens. This part with the nitrogen is an amine group, and this section over here with the 2 oxygens is a COOH. That's an organic acid group. So this guy is actually an amino acid, and that will occasionally show up on the final. They haven't ever asked anybody to name the amines or the amides, but basically for amines, you count your carbons. This amine is your ending. The number is the location of where the nitrogen is. For the amides, you do the same thing. You just count the number of carbons, and anamide is the ending for the amides. That should be enough background, and we will practice naming each specific category during the lecture notes about those specific classes of compounds.